All right. Okay, so good morning to those of you who decided to show up. I got 6 at half. Ah, here we go. Okay, so on Blackboard I've posted your lab and everything you'll need. Lab 1, I will update that to indicate April 7th instead of March 7th. But basically, what you're going to be doing is you're going to be going through step by step. You're going to read through it, and it's you basically open file, open library. You're going to follow the steps and just read through it. And I've given you, directions on what things should look like when you're done using the electric Vlsi tool. This is the way you should be filling it out. I've included lots of notes to give you good directions, such as File, Save, Control-S to save your library, and lots of little notes. I've included some Spice code that you want to put in there. Also, in bold, I have descriptions of what I want you to do step by step for your lab report. So as you're going through and you hit that point, you're going to tell you what I want to do. So here it says, in your lab report, copy and paste the generated code. Next, describe the code in your own words. Be sure to use the TGOs as reference in describing the code. So you can actually, at this point, you're actually going to be using the electric Vlsi tool to generate a Spice file, which you're then going to use in WinSpice. So then I want you to actually look through, because it's not going to be commented, so you should be able to understand what the code is actually saying. And here I say, click on this, and you click on your ivcurves.cir file. You'll get a window like that, and then you actually follow directions, and you'll be able to generate IV curves like we've learned about. Then the next thing, you're actually going to be drawing a NAND gate. Provide a screen capture of the one that you do. Switch level simulation. You're then going to actually simulate it. You're going to print a waveform. You're going to do that. So then next, you're actually going to start creating a little cell. You've created a NAND gate. So then you're actually going to take care of this. Then you're going to simulate it, and you're going to see the differences. So at the end, in red, I have Lab 1 report expectations. So this is what I'm expecting from you in your report. First thing, you're going to put your honor statement. You're going to put your names and your group name. So group name, for those of you who had me 385 last semester, be creative, have fun. Some of my like Team Ultron and all of the unspeakable things that Thomas's group wrote in their reports. I would read your reports and go, they feel tortured. This is sad. This is not going to be as work intensive. The size of the PDF is mostly to provide as much detail. So walking through, you're going to be learning. You're going to actually generate a Spice file based on a created circuit, and then you're going to simulate it and produce waveforms in this particular lab. The next lab, you're actually going to do a cell, and then you're going to start working on the data path. Now, this electric labs file is a zip file, which I won't be able to open here on the iPad, but it has all of the code that's referred to. It's going to be in labs 2 and 3. So you're going to take code, make minor modifications to it, which I'll be going over in these next few lectures, precisely how to do that. So what we're doing in lectures is going to correlate to what's being done in the labs. And then from there, eventually you're going to be doing an actual synthesis, and you're fix the controller, you're going to fix the data path, then synthesize it. So you're going to generate a layout, you're going to put it in a pad frame, and then you're going to do something called tape out. You're actually going to put it in the pad frame, tie it to the pins, and do that. So by the end of these 3 labs, you will have made your own computer from the gate level up, and it's a little more simple than what we did. So let me go back to the steps. 2, you're going to complete all the TGOs, so we'll finish section 7 today. Section 3, in a couple of paragraphs, research and describe who invented electronic logic gates. There's a little bit of debate about it. You'll be kind of interested, particularly who invented the electric AND gate. So that's kind of knowing and understanding the history of computing. Describe the process you took for each step. So don't just do screen captures. You should kind of briefly write up what you're doing. Simply keeping the screen captures is insufficient. The goal should be, you think of this as you're writing the lab report. You should be able to reference this in 1 or 2 years as you're preparing for a job interview and know precisely what you did. So if you can describe it, what you did to get to that point, then that'll be good enough for a really good score on the lab. At the end of the report, this portion, to writing about the challenges you faced, things that you struggled with. I read these over, and that helps in the event that for some reason you might not finish the lab or you run into some sort of real challenge, that if I were to add something to the lab next year, other people in the future won't have that problem. And that's good. I've added writing fluff doesn't meet that goal, so as you guys have learned from the reports that you guys did for SemiWiki, which I finally got the last picture, so I'm going to be sending those over today, and they'll be posted, at which point they'll be interacting with you guys. So, but generally, the goal is describe what you felt was a challenge to you, or anything else interesting that you learned. Like, oh, I never knew that. That's interesting. I was playing around and did some other things, and I go, that's good. We'll be going over the creative process today at the end of the lecture. So I want you guys to find this interesting and kind of have fun as well as finishing the test. And then upload your PDF lab report and your generated files to Blackboard and zip files. That way I can review your work. So I will fix this. I know it says March 7th on the top, but I will fix that later to say April 7th. So this is going to be due each Tuesday. I've posted the last 2 lectures on Blackboard. As I've said before a couple of times, you are permitted to type the TGOs for the lab reports. Does anybody have any questions on the lab report before I go back to lecture? Yes, Jason.
Whenever you say upload to Blackboard, will there be an assignment that we click on?
Yeah, I will provide that.
Okay.
Yes.
What about the groups?
Yeah, you have the same groups as you did for your SemiWiki. Any other questions? All right, awesome. So real briefly, I have corrected the TGO numbers from last lecture. The level 1 Shockley model is 7.25. The variables, the brief description of SPICE level 1 is 7.25. I had this listed as 7.26. That relates to these equations. And then the body effect relates to what is now 7.27. 7.28, I describe the level 2 and level 3 models and how those are improved by using subthreshold conditions in Dibble. 7.29, description of what the modern Berkeley short channel IGFET models are. And then 7.30 was the definition of Monte Carlo simulation. 7.31 is the basic syntax in SPICE of the Monte Carlo analysis, so sweep and Monte in your keywords. 7.32 is now .ic, the initial condition command. 7.33 is now the formats for your uniform distribution and a Gaussian distribution functions. I had a couple people ask what relative and absolute deviation were, so I thought I'd include that just as a little note here. So relative standard deviation is your deviation over your average times 100%. So gave 3 examples, 100, 100, 100. There's no deviation, so 0 over 100. 100, 90, 110. So from the median, the standard deviation is 10 and 10. So that's 10 over 100, 10%. And then this one, the median is 10. So the standard deviation is 32.90. And the average is 27.85, so the deviation is actually 118.04. And the absolute deviation is a data set or the absolute difference from the element of the given data point. So you have an element and a given data point, and so you have the median and the chosen measure from your central tendency. And then we did this. I presented this spice file where we actually generated resval using your absolute universal distribution, 140. So those are the two values you put in. And then we have the RC circuit, and then we generate transient analysis, time slice, total time, sweep, and your Monte Carlo analysis is 10. So now we want to go to generate this worst case in Monte Carlo sweep example. So this is where we stopped last time. So basically what's going on here is we have measure the delay and power consumption of two inverters. So so we got our macro. So I want to point out dot macro and dot EOM. That's the same thing as sub-circuit and ends. So those are synonyms in there. I also have that there. So basically the netlist contains two sets of transient analysis parameter sweep from -3 to +3 minus sigma, and a Monte Carlo analysis. It creates one set of output files for the sigma sweep and one set for the Monte Carlo analysis. So we're going to actually produce two sets of waveforms, and I'll show you both of those in a moment. So we've set a parameter. We've initialized sigma as 0, but when we do a transient analysis, that's going to change. We've defined voltages, and we have a set of inverters, at which point we've done a macro where we define them all. And then we're actually defining a number of these different terms using Gaussian analysis. And I will show you those waveforms in a second. Here they've actually defined the NMOS and PMOS in the spice stack. So like we showed you in level 1, instead of doing a dot include, they've actually included the actual information there, the actual models there for you. And then transient analysis, normal transient sweep sigma, 3, -3, and 0.5. So we're measuring delay and power. So we trigger when node 2, which if we go back up here, we have in an inverter, and then 2, and an inverter, and then 3, and then 4. So this is in 2. So we're checking the voltage here. And then the target is out. So we're checking here with fall, and that's going to invert twice. So then we're checking how long it takes to fall again. So that's what we're measuring. And again, we're measuring that power consumption. Root RMS, does anyone know what RMS stands for? Any guess? Root mean squared, that's correct. And then again, we're going to be checking the delay here for S delay and R delay. So, and for our transient, the probe, this is the second value we're checking, Vn, V1, V2, V3, and V4. So the first plot is going to show the transient analysis, and this is going to be sent to inv.tro. So all of these values, all of these values that we measured here are going to be plotted in this figure. So if you were to go, and this is an example, this is actually a synopsis. So if you press these here, this will expand all those out, and all those values are going to be the values that you defined in your spice stack. And so then based on your delay, you're actually going to be able to see time versus voltage. And then the second plot is actually going to show your power and delay. So what you're measuring based on your Gaussian analysis here for the Monte Carlo, with a change, and it's measured -3 to +3 sigma, right? So based on the sigma values for your Monte Carlo analysis, you get a steady increase in power consumption and a steady decrease in delay. So that's how you can use the Monte Carlo analysis to be able to get all those kind of values. Okay, does anybody have any questions on anything we've covered before I kind of go into this computer aids for VLSI design? So this is actually, you're actually going to kind of learn some premises of actually using computer-aided tools like Electric VLSI Designer, like WinSpice, to be able to simulate and design circuits. So up to this point, you've done everything by hand on exams, and you don't want to do that for billions and billions of transistors. Have a computer help do it for you. So computer-aided design, actually I probably should have stopped. Does anybody actually have any questions? All right.
Could you go back up to the TMX and all those parameters real quick? I just want to take a look at it.
Sure.
The A-Gauss note one, I get what again?
Yeah, let me scroll up for you so you can look at the definition. So A-Gauss is Gaussian distribution function using absolute variation. So you have uniform distribution and Gaussian distribution, and from each of those you can have a relative and absolute variation. And so the way you would code it in are these four. So you name the parameter, parameter is XX, and then it equals A Gauss. So this is the one that's being used in there. So they have the num sigma, the nominal value, and the absolute variation. So let's go down to the code and take a look at it. Nominal value, absolute variation, and sigma. And so actually, a kind of a neat thing, you see if you have the dot param, instead of saying dot param every single time, you can use these plus marks to define new parameters, all within the same line of code. Does anybody else have any other questions? All right, so computer-aided design. Computer-aided design, we define formally, is the use of a computer system to assist in the creation, modification, analysis, or optimization of a design. So you've already seen some examples of this where we did the PN ratio. We've created the design. We modified it. We've learned ways to troubleshoot so that way we don't do simulate and tweak. And analysis, we just did some Monte Carlo analysis, and optimization, we've done PN ratios. So you can think of when I say that CAD systems are translations, you have different levels. So you have spice code, and then you have polygons, right? So you have some sort of circuit, and then here you can, NAND is actually got an M0, MN0, MN1, MP0, MP1, and so forth, right? So you have to have some sort of translation. We remember that we were talking about the design rule checks. We bridge this gap by using stick diagrams, right? So you learn the stick diagrams to lay everything out so you know how your circuit should look. And then from there, then you can use that code in HSpice to simulate it. Or if you want to use something like Cadence Virtuoso Designer or Electric VLSI Design, you can actually see the layout and lay it out in the way that the designer has, that the tool dictates. And we'll go over some examples of that in later labs. Two things that I really want you to know about are Asics and printed circuit designs. Asics stands for Application Specific Integrated Circuit, and they're integral circuits customized for particular use rather than intended for general purpose use. So Mips is an example of a general purpose use computer. Right? So you take some code that you write, compile it down, and then it runs on the Mips data path. Application-specific chips are basically, you encounter hundreds of these every day. You get into your car, you have a number of different sensors. All the chip's doing is doing that one task. That allows you to have smaller overhead because if you remember back from when I had reduced Mips data path, right? Give me a reduced Mips data path that does R-type and low work. The purpose is that you should be able to identify portions of the circuit that are not needed for those instructions and write them out. So at application specific, you're taking that fundamental that you learned in that problem and extending it a step further and saying, I'm only going to design a circuit that does what I need it to do and nothing else. So that's application specific integrated circuit. So the next one is a printed circuit board, which results in the precise positions of conducting materials as they will appear on a circuit board. So this is an example of a printed circuit board. And so when you fabricate it out or you're designing it, we can actually, if you were to flip this over, so you have your input pins, and that's the circuit's actually going to flow through the way you kind of lay it out, the top of the bottom, based on the way you can solder it. And you can actually use this to actually kind of provide a macro level of what's going down on like a transistor level. So the system design process, I've alluded to it, but there's two major types of system design processes. There's graphical and textual. So textual, SPICE, we've gone over that in class. VHDL, you did it in advanced digital systems. Verilog, you've done some of that so far already in this class. In graphical, you're going to learn Electric VLSI Designer. Another common tool is Cadence Virtuoso. That's the one that if you want to spend $1 million every year to use it, go ahead. Or you can use the free one. So what do you think are some of the pros and cons of text versus graphical? Speed of what? Oh, okay, I see what you're saying. Like you're trying to render graphical. Okay, right. So processing speed is important. So you're taking some sort of text and you're compiling it. We'll learn about electric compilers. Compiling it down to the DRC level, at which point it simulates. However, the graphical, what do you think are some of the advantages of graphical representation?
Easier to look at.
Yeah, easier to look at, easier to tell how everything's laid out. Have you laid it out properly? Like remember we did the measurements for wires, where you said if a wire is a certain length, and it's a certain distance away, so we've created a capacitance effect, and the resistance of the wire is based on its length, right? So that ultimately ties into its power consumption. If you have some sort of circuit over here and some sort of circuit over here, like, okay, well, I can actually reduce the power consumption by just taking that cell block and moving it over. And that's something where if you're doing this at the textual level, you're dependent upon the compiler to do a lot of that for you. If you remember in section 1, I showed you the difference between the designed Mips versus the synthesized Mips and how big the difference was. That's kind of a lot where the graphical versus textual implementations come into play. So here I've given some examples of the some graphics. So this is the actual graphical representation we saw in section 1 of an inverter. And here is a textual representation that we've done earlier in this section, where we have our inverter MN0 and MP0. So we have our NMOS and PMOS, and we've done our sizes. Here we can actually physically lay it out and make modifications and optimizations as we see fit. We can't quite do that here. However, you can compile this and run a simulation as well, but it's a lot harder to find an error. So, for example, think back to that problem I gave you in section 6 where it was the XOR with a stuck at 0 fault, right? Or for now that you guys have completed the exam, the stuck at 1 fault for the subtractor circuit. And you have multiple instances of the cell. If you're just we're going to go over flattening here later today, but if you flatten it out and you're just looking at a larger version of this, finding the specific faults can be difficult. Especially because when you run the design rule check, it'll just show an X somewhere. It'll say, hey, this is where we think the problem is, but that doesn't necessarily tell you what the problem is without troubleshooting. So those are being able to find that issue in a textual representation can be a little easier. But using this allows you to be more creative in your design layout. So, and this is kind of a design flow here of graphical versus text editors. text editor, you have your textual database. So here you have your .include file, and your graphical database, you have your DRC. So here you're going to actually plot your simulation based on your write-up. So you write up your code and then plot it, and you see if it meets the product specifications. When you do a graphical database, you're going to plot it, and if it doesn't work, you're going to reformat it based on your original design. So the graphical database is based on cells, and textual database is your and cells and DRC. And so we're going to learn about different levels of hierarchical design. And again, they all have to meet production specifications. So eventually, everything you do in design has to meet what the customer wants, right? So we've learned about Spice, we've learned about Verilog, and then you're going to have analysis tools where you run your waveforms. 385, it brought up those green waveforms, and you were able to see whether or not it was working properly, but it didn't really have much in terms of power consumption, right? Here you can actually code into the textual diagram what will actually run. And for example, in Cadence Virtuoso, you can actually have a graphical layout and have it generate a huge spice list. The spice, because it will actually recognize where your transistors are. It'll know different metals, it'll know different types of circuitry, it'll have all the physics accounted for in the DRC. From there, you could actually run simulation. The analysis tools are what we do to use the simulation. We find them formally as being used to detect local layout errors, such as design rule violations, and more global design errors, such as logical failures, short circuits, and power inadequacies. So we've now seen descriptions of all of these in previous sections. So hopefully this is all starting to tie in. We have our initial editor. So electric VLSI design. And then you have some sort of database where you have your design rule checks and the underlying physics. And so basically, you're kind of going on a loop here until you're complete. Right? So the TGO is this definition here. Analysis tools can be used to compare different versions or different views of the same circuit that have been independently designed. Now, what this means is, and this diagram is actually a really good example of it. So let's say here we are using, one of them we use a data path, one we use programmable logic arrays, and one we have an ASIC, right? Pros and cons: power consumption, area. We would be checking all of these things: power consumption, area, power inadequacies. If we use an ASIC and we don't have the circuit isn't properly designed with output capacitance and power consumption, and we can't drive the next thing that needs to be used, your ASIC is going to drive some sort of detection tool. For example, a very common ASIC in cars is you have some sort of computer chip that's a sensor. It's reading everything that's coming towards your car. And the objective is, if I'm in the car and I'm coming towards Thomas, right? Thomas has and his pencil's an ASIC chip. It should be reading how fast I'm coming towards him, right? And it makes a calculation in it. If you think there's no way that I can slow down before making a collision, it will then send out a signal to the airbag to deploy before the collision takes place. So if you're not properly driving the power consumption to the next on that signal in order to get up to the airbag, then you haven't properly designed the circuit. Whereas using a data path or a programmable logic array, while you might get more area overhead, may provide some sort of power guarantee. So by using your analysis tool, you can have 3 different designs and compare them simultaneously to see which design you want to pick best. And you can do all of this before sending anything to Foundry, which becomes important because now you've significantly reduced the cost. Because you don't send out a chip, you're obviously going to test the chip when you get back, but you want to thoroughly test it before you send it out, which is why testers get paid so much. I remember I said a few lectures ago that testing is half of the cost of a chip, and if you're really good at testing, then you can be very valuable to a company. That's another method of doing it. So I've kind of alluded, so we have some textual, we have these graphical analysis, and then we do our simulation, right? And so we have to have something that actually kind of describes all of this and is a tool that gets us there. So it takes all the information from you and actually runs the simulation. And these are known as synthesis tools. So the synthesis tool, if you're coding in VHDL, for those of you in 386, and putting it down to a board, it's going to take your logic and put it to a programmable logical array, right? Because that's what your embedded systems are designed in. If your ASIC is going to use your cells and your underlying technology, trying to make it as small as possible and power efficient and optimized. That synthesis tool takes specifically what you're designing it to and accomplishes the task you want. So we've defined it formally as they're being used to perform repetitious layout, such as programmable logic generation, complex layout, such as routing, and even layout manipulation, such as compaction. So smaller area, you want to route it properly, so that way you're meeting all your design rule checks. And if you're using PLAs, you can actually synthesize it to any board based on the synthesis tool. So again, you have your text editor, you have your high-level specification. The high-level specification, what am I programming it to? Am I programming it to a board? Am I making an ASIC chip? Am I trying to make some sort of PCB? From there, you actually synthesize and get the result, and then you're going to reformat it. And then if you remember from 385 and 386, you're starting to build this giant database of code, which you can then reference later. Once you've completed it, you can add that to your database, which you then can use for subsequent designs. So here we've talked about synthesis tools. This particular concept of a silicon compiler is specifically compiling, and Cadence, Virtuoso, Electric, VLSI Designer are examples of silicon compilers. You have some sort of physics, some silicon-based physics, and your entire 8-FET Berkeley model has all those details, and it takes all that information plus your SPICE code, and then plugs it all in and gives you an actual circuit layout. It can tell you the power consumption, it can tell you where things are going right, it can tell you where things are going wrong, usually very, very accurately. Right? You want to try to thoroughly test it. If you can do it in different ways. You can use your built-in logic block organizer to surround your circuit to test everything. You can use your D algorithm and in order to generate a minimal set of vectors that can test all the possible stuck-at faults. And you can do all this, but your silicon compiler needs to do this first, because you actually have to have the integrated chip, which you can then use your graphical tool to render. But the silicon compiler is an important step in this process. So it's a software system that takes a user specification and automatically generates an integrated circuit. What's that? No, Vivado is more of a synthesis tool that goes to the board. Okay. That's a good question. That's the difference between a typical synthesis tool and a silicon compiler. A silicon compiler. Let's see if the next I have it. Well, I got the silicon C to silicon compiler from Cadence description here in a minute. But you can. In there, it can actually compare all of these for you, right, in the process. It's basically all it's doing is using the library. If you want to put it in a data path or you want to do it ASIC or a programmable logical array, you can take your high-level specification. This can be SPICE. This can be VHDL, Verilog, and it's going to analyze it. And then based on that, it will generate a set of circuits. This is based on these, it'll you have some sort of routing specification, and specifically the customer has demanded specific design constraints, area, power consumption, and cost. You can compare these, you get your results, and then from there, we've done this concept called pad placement, which we're going to be going over a little later today. So you have a circuit, and then you're going to place your pads around it. The pads are going to say, all right, so your pad V in, input A, input B, V out, ground, and all of those go to your, or come from your integrated circuit. So here, the final circuit is generated from your silicon, since we're talking about the silicon compiler. So this is combined kind of all the concepts from that we've gone over earlier today. So does that make sense? Want me to? I can zoom in a little bit so when you're reviewing on the video, you can look at it. So here I've provided the data sheet for what's called the C to Silicon compiler. This has been designed and is sold by Cadence. And so they have their format descriptions. They use IEEE System C as their input design language. And there it compiles it down. And its output design language is IEEE 1364 Verilog, which you guys have learned this semester. And so it uses the synopsis design constraints during the synthesis process. The graphical user interface has an RTL schematic viewer. They call it the new design wizard, which is either some fancy tool or they actually have a little man inside there doing it for you. Control data flow graph, right? So it's going to take your code, generate your you can use it to view your critical path. Remember, we did critical path problems earlier, so you could have to put in buffers if you're having some sort of race condition. Area and power tree maps, resource viewers, and RTL register transfer language schematic viewer. Embedded logic synthesis, so if you're trying to do, remember Xilinx or Altera, this is kind of the same thing as Vivaldo. And ASIC Cadence RTL compiler, so you can do this down to Verilog. And Spice. The specific version for Cadence that they use, they call it HSpice. Analysis, it has built-in timing power analysis. You can actually use this to generate your waveforms like we just discussed. It has a full database for different technology files. You can do clock gating and memory support, design RAM. We'll be going over that next week. And then you can use all these different functions to try to design different aspects of a computer. And then also, you can automatically generate test benches and simulate models. So from 385 in this course, you now can do almost anything. It also provides self-paced tutorials. And one of the reasons, this kind of ties into one of the reasons why I had you guys do the Verilog on your own. One of the things I got back when I asked the question in industry, what do you want from potential employees? The thing a lot of them said over and over again is willingness to teach themselves. So on resumes, you can now say that I'm an independent learner because you've done it. You've taught yourself Verilog. Right? So, or for those of you who are just smiling, oh, maybe I didn't, maybe I did. I did see that. No, but
I heard everyone back here talking about it.
No, but I mean that's my point is, I'm not just doing these things. I hope you don't feel tortured, but there's a method to the madness. Ultimately, if you're the type of person who can teach yourself Verilog, you're also the type of person who can follow the self-paced tutorials and use the Cadence tools quickly. So ultimately, and you also have proven that by going through these 3 labs. So also, if you recall your Gatsky and Kahn chart, you now understand all aspects of this. We've now covered everything in these 2 courses. So you now know what polygons are. The polygons, we use those to design, to meet our lambda and our design rule checks. From there, we use sticks to do the layout, to try to actually do the layout from the logic. Standard cells, we use those to build the standard cells, which we will then put together to build. We learned in more detail than you probably ever wanted to what a transistor is, how you use those to make gates. Now you go up to the RTL level. Now you're using synthesis tools to design your processor, your memory, and your switch. You've learned differential equations and Boolean equations in previous math courses. RTL language, you learned that in 385. And then algorithms are a set of steps of problems to solve a set of steps to solve a problem. So you've kind of learned all of these tools now in your Gasky and Con chart. So this is kind of a basic overview of the Mips data path. You have your controller, ALU controller. If you recall, it's 2 bits, and then you have a bunch of control signals that are going back and forth between the data path. From here, we're going to do our layout. Right, so this is our pad frame layout. So here you'd have 10 I/O pads, and I'll show you what this actually looks like in a second. And then you're going to have your data path and controller. So I'm going to zoom in here. You now understand what this means. Now you 2,550 lambda. So now you translate this down to your technology file. Right? Somebody's very, I get it now. Right? Height determined by programmable logical way, size, widths, and data path. Wiring channels. This has been calculated, and you know how to do that. And also, you know the actual calculation of the data path. So they tried making the data path and controller the same width, and then obviously the data path is going to have a different length. And then from there, we take this layout and actually generate a circuit. So this is what your synthesis tool does, specifically your silicon compiler. By the end of the 3 labs, you'll have one of these of your own. And so you have the pads, and you see how they actually connect in. You have your controller and your data path. That's what they actually look like physically. Okay, so does anybody have any questions before I continue? So how many of you are familiar with search trees and graphs? Right. So you're kind of familiar with some of these terms already. A cell is the lower level of design of a commonly used logic block. A leaf cell does not contain of any other instances, and it's at the bottom of the hierarchy. So typically, say NAND and XOR, right? And OR. And here you can make full adders, and you have one full adder, and then you can make an entire full adder. And based on, you can include multiplexers, you can include Kogi-Stone propagation logic, and you can use that to build any kind of adder. So all of those kind of build up to different levels of cells. The root cell is your top cell. This is ultimately what you're designing. So here, in this case, it would be full adder. In the previous diagram, it would be the entire Mips data path, of which it breaks down into data path and control. And those break down further and further. Now, an instance is a use of a cell at a higher level of abstraction. So this is an example. So the cell is your D flip-flop, and then you're using this logic to propagate the signal. So this is a kind of an instance of an up counter. So then down here, this design is put into each of these. So this is the instance. I'm sorry, this is the instance, and this is the lower level cell. Now, this is where the design challenges come into play. So a circuit with no hierarchy and has a depth of 1 is said to be flat. So what you're going to want to do is you're going to have different cells. You're going to test it, and then once you test it, then you flatten it before you move on. Where that problem comes into play, if you remember from section 6, I've given you this example of the full adder with a stuck at 0 fault. Here's why it took so long. Now you know enough to know the struggle. They designed the circuit out, they designed it with polygons, and before they tested it, they flattened it. And their cell for the XOR was shorted to ground. So now it's a big layout, you don't know exactly where it is, and you get wrong results. So now, instead of taking a few steps back and figuring it out, now they're going, well, what is it? They dig into every little part. They fix this. Well, guess what? They still get wrong things. So then what they do, they go back to the initial thing, and keep going. And so the design principle is keep it at the cell level, test it, and then once it meets all of your tests that you set out, then flatten it. That'll save you hours and hours and hours of time and hair if you're the type of person who rips it out. Okay, does that make sense? That's the reason why I've been jumping up and down, because I want to save you guys that kind of trouble. So next thing I want to talk about is, did I include that? Oh, I think it's a little later. So anyway, one of the benefits, I'll kind of allude to it. One of the benefits of understanding leaf nodes and all the hierarchical organization, if you recall, branching effort, right? Branching effort is based on the number of subsequent elements in the path that are based on the particular fan out, right? And so, excuse me, that branching effort contributes to the branching effort contributes to the path effort. And so, if you have a lot of branches in your design that's driven by that, let's say you have 85 adders that drive one element, that's bad because now you're adding to your path effort through branching effort. So having an intelligent way of doing a hierarchical organization and design will ultimately reduce your power consumption and improve the quality of your circuit. So good design fundamentals will contribute to better circuits. And so you guys should already be familiar with the concept of top-down and bottom-up design. And so I've kind of given an example here of a top-down circuit. So the idea is we're designing an absolute value circuit. We have two inputs, A and B. And so the first level, you'd have a subtractor, a test circuit, and then a negation. And then here you'd be breaking these down into different, you have a complement and increment, negation and adder, and all of these continue to break down, and eventually you'd be getting to XORs and NAND gates, right? So that's a concept of top-down design. And the opposite is a bottom-up. So here, we've designed a 4K memory chip. We design the 1 bit, we make that a cell, and then next step we know we eventually want to get here. So next we're going to make it into 8 bits. We make this into 32 bits by using 4 8-bit values. For those of you who took my 385 or CMOS, what kind of memory addressing is that called? What is that called? What type of addressing? The byte addressing. There you go, right? So now we're seeing physically why byte addressing is important. So then, for those of you who remember, load word, you multiply it by 4 times the current times S0 and so forth, right? So now we're putting a bunch of 32-bit values, since these are our elements, into our data memory. Here's just an example of 256, right? So now we're talking about cache organization, and we're talking about memory hierarchy and why we use different. We have I can't remember the word. Direct and set. Kevin, make yourself useful. Remember what the word I'm forgetting. No, but so you have if your memory hierarchy, so you're relating it back and forth. So you have 4 blocks, and then what you're going to do is you're relating different levels of the cache, and then you swap them back and forth, right? So this is how you build those back up, and you learn that and you optimize that based on. Now I've psyched myself out. Temporal and spatial locality. Associativity. Come on, Kevin. You're supposed to remember that before I did. Direct and set is associative.
Yeah, I knew it. I didn't want to say anything.
You didn't want to psych out Kevin, steal his thunder?
I'll steal his thunder all day.
You guys can do that outside of class. You made assumptions, not me.
surprised it took him 2 semesters to figure that out.
Oh. No, but getting back to lecture, so you understand how that builds up, and all of those builds are based on design choices, based on power consumption, area, and so that's the result of the memory, the data memory in the Mips data path is a result of a bottom-up approach. And so kind of alluding to what, now this is what I was alluding to earlier, branching factor is the average number of splits that are made at any point. So here, this is some sort of number of bits. If we're talking about our absolute value again, we're going down each one here. It's the split is 1, 1, and then a number of bits in the complement, right? So the branching factor is defined as 6n plus 9 over 10. That's for the number of bits in each part. So if you have a 32-bit data path, you make that 32 because that's the number of bits you're doing in each calculation. So ultimately, if you don't control your branching factor, that contributes to your branching effort, which contributes to your path effort. Does that make sense? Awesome. And I've kind of included the definitions of branching effort to kind of review how that ultimately ties back in. Does anybody have any questions before I move on? All right, so layout overlap. So this drawing here is, this diagram here, I'm going to scroll up to there so you have the TGO and the, so we define layout overlap formally as an instance where functions of two components are different enough to place them in different subcells of the hierarchy, yet their relative placement in the design is very close. So here we have our cell, right? And we've put in our 4 copies of the cell. When we synthesize it, we're actually going to be reducing it because we're going to be having some sort of VDD or ground or shared voltage source based on that cell. Your synthesis tool will optimize the size of the circuit based on the layout there. So normally you'd have 4 cells and you'd have to connect them, which creates wire lengths. But you can, if you realize here that, so you have these cells, you see how it's actually, I can zoom in so those of you in the back can see what I'm about to talk about. You look at, here's the original cell, right? So you see you have the 2 overlap axes at the top and 1 at the bottom, right? And so the overlap axis at the bottom has 1 pin and 2 pins at the top. So now, here's what happens. You see how they have they've combined the pins logically in such a way, so you could use this is a good design of a mux, a 2-to-1 mux. So now you can make 4-to-2, and then you can have your output 4-to-1 based on this layout. So by flipping these 2 around and putting it together, you significantly reduce the area of the layout. So this is where a graphical interface would be helpful as opposed to just a textual interface. And so that's taking advantage of this concept of layout overlap. So when I took CMOS as an undergrad, I used this concept of layout overlap to really reduce the size of the multiplexer. We had to design a temperature reader, so we had an 8-bit input, and then we had to do 8 comparisons. So we had to do a 64-to-8 multiplexer. So the 64-to-8 multiplexer ended up taking up a lot of space because people kind of didn't take advantage of this principle. So you see how it, you almost cut down the size of 1 here from 5 to 4. So if you really, if you're doing it 64 to 8, you're cutting down significantly on the size. So that's a good design principle to use if it works. Now, if you're overlaying them and you get bad results or you're shorting it out to ground, that's when you create problems. So I also want to talk about parameterized cells. We kind of have already we've talked about the idea of parameter cells a number of times in class already. First, we talked about in section 5 where we designed these two AND gates where you had two 4 to 1 4-input NAND gates, right? And we had AND gate, NAND gate, and inverter. NOR gate, NAND gate. Then we designed this AOI 22 gate, and there were trade-offs between path delay and effort and area. So parameterized cell, it takes these customer constraints in your synthesis tool and says which one's better. If the customer says the thing that we really need this chip to be small, and so you can, what it'll do is it'll see area, and then it'll put your gate in that way. If it's path effort, delay, power consumption, it'll be this circuit. Another way we've talked about parameterized cells is in the sub-circuit command in SPICE. So that was about inverters where we initialized the parameters as 8 and 4, but then we were able to change the size of the NMOS and PMOS based on the output and input capacitance. And we calculate that using a fan out of 4 inverter. Let's define parameter size cells formally as cells which can be instantiated differently according to their environment. So you don't want to use the same cell for everything. You don't want to have to create 40 different cells when you can just use parameters, and your synthesis tool will update the parameters for you, or your synthesis algorithm if that's who you choose. So does that make sense? So this is kind of a lot of how does the tool do the things that you guys have already learned? No. Okay, so now we're going to talk about connectivity. So here I'm going to talk about an implicit constraint on VLSI design is that everything is connected and that the connections carry information about the relationship components. So you have a set of inputs, you have a set of outputs. You have, let's use Mips data path as an example. You have control signals, you have a data path, you have memory, you have inputs and outputs. The inputs and outputs can come from I/O devices. Outputs go to those devices or to your main memory. Everything is somehow connected. You have a data path flow, right? What we mean by connected is that you have your. I'm not saying that the program counter is connected to the data memory directly, as it used to be in the tyranny of numbers. Remember I talked about Jack Kilby? I'm going to talk about that down here with the tyranny of numbers. What it means is the program counter is connected through the instruction memory. The instruction memory is then connected through the registers, which is then connected through the arithmetic logic unit, which is then connected to the data memory. So that's all connected somehow. Two separate circuits will never, there's no wire between them to do anything. So that means everything in the circuit is somehow connected. For many VLSI system designs, the nodes of the network are components and the arcs are the connecting wires. So here are FSM, state 0, state 1. And then if it's 0, go here, and if it's 1, stay. And if it's 1, go here, and it's 0, stay. Right? Simple. The nodes are making the decisions, and the wire and the arcs are connecting. But some systems reverse this view where the edges are the actual, because the edges, especially in Mealy machine, which I'll show you down here in a second, represent some sort of design, and then the nodes are where you could potentially make it just where you're going to go here or go here. So the wires are represented by the nodes. So from section 1, I talked about the tyranny of numbers, right? We talked about every component was connected to every other component, and then Jack Kilby came by and invented the integrated circuit, and as a result, now instead of having everything connected, you can have a data path and a control, which significantly reduces that. And then we used silicon-based devices to slowly using transistor sizing, reduce the size of those circuits. So before this was why computers weighed 2 tons and everything was connected to one another. So this is the Mealy machine. This is actually, as a historical note, I went to the paper. This is the original Mealy machine that George Mealy presented when he derived this, and this is a PDF that you can reference to take a look at what he actually did. So let me ask you this question. So here we have, before I ask you the question, here we have nodes and edges. We have different designs, 1, 0, 0, 1, and so forth. So let me ask you this question. If you're trying to design a circuit that does this FSM, what are the trade-offs between top-down design and bottom-up design? If I'm your customer, I've come to you and I've said, hey, this is my circuit that I want. Make it, please. What are some of the trade-offs?
As far as what goes?
The design process.
I mean, specificity, for
Mhm.
sure. Definitely power trade-offs.
Specifically where?
Specifically,
You're on the right path. Right? This is kind of what I want you to do.
Leaves.
Yes, exactly. So you got your leaves, right? So inside S2, you actually kind of have to make a decision. Am I going to figure out what this logic does at the lower level? And once it does, I have to figure out my cells that meet that node. So that's your top-down approach. Or from your bottom-up approach, you can design those cells, and eventually from those cells, you can put those together to try to for reuse. So the problem is you're going to have different ways of branching factors for these decisions.
But that's only limited by your employer's knowledge, isn't it?
By the customer constraint, because hopefully your employer and you are intelligent.
That's what
If your employer is stupid, you can present this as a possible solution, and then you're part of the patent and you can feed yourself a lot of money. Which is actually, after this TGO, that's actually a really good allusion to the last thing I want to cover today. Smart you. So, but that's the right answer. You have to worry about area and power consumption trade-offs in your top-down and bottom-up design. So you can use your synthesis tool to, as we kind of learned, you can have different ways of implementing using a data path, DLAs, application-specific chips. From there, you do your top-down or bottom-up design to figure out what cells are better, and then from there, you can make an intelligent decision about what circuit you want to do. So here I've kind of alluded to this last one. This is the second to last TGO in this section. What is the concept of a net? A net is a single electrical path in a circuit that has the same value at all of its points. So this is a net, this is a net, this is a net, and that's a net, right? So here, the way we do this in SPICE is we would say the two inputs to this AND gate are in and out because this feeds back, and then we have a net connecting them, connecting the NAND gate and the NOT. So this is kind of an AND gate design with a feedback path. So what, kind of reviewing what we learned yesterday and very briefly today, if I wanted to simulate this, what command would I want to put into my SPICE to ensure I could simulate every instance for feedback path?
Monte Carlo?
No, well, not Monte Carlo. No, I'm specifically talking about the feedback path. That's my big hint. If I'm doing set of inputs, what's the problem with the feedback path?
You can't set it.
And how would I set it in SPICE?
It was the command you told us last time.
It's on the tip of my tongue. I would set it to a blank value.
Global?
Not global.
Can I call it?
If you're going to set it what to your
Is it A?
no, it's. I'll give you guys a couple more seconds to figure. I don't need to set it, because once I have a value and it runs a couple of times, the feedback path will provide the next value. So if I have all but the first one, what value am I missing? Initial condition, that's the name of the command. .ic.
I see.
Yeah, it was on the tip of your tongue, Tanner, I could tell. So now so here you have your net, you have your .ic command, you set it v out is equal to 0, therefore you can simulate it. So you have your output, and this is kind of known as an unnamed net, because it's going to add this wire. It can drive the output, but then it also is provided as a feedback due to your SPICE condition. I'm sorry, your SPICE code. So when you hear a lot, especially when you get error messages and you net 48271, it'll render that error message, and you go, what the hell does that mean? You go into your SPICE code and you look down, and it'll actually indicate what net it is, and you'll know the exact location of your fault. From there, you can use your graphical reference and you use your textual reference. You compare them, and you go, I shorted my XOR gate. And then you're done. Okay. So, this number is going to be 7.47. This will be the last one, and I'll tell you what parts of this are not to be included in the TGO. So you've now learned all these aspects of CMOS design, but eventually you're going to be asked to make something new that no one's made before, right? So I had the opportunity to meet Raphael DeLuzio when I gave my talk about the TGO method up in Princeton. He talks a lot about engineering creativity. So we're actually going to be trying to work together, because he was saying that he works on creativity, but the thing that there still needs to be engineering fundamentals. My method works really well on developing engineering fundamentals, but I struggle with trying to figure out how to be more creative. So we're now tying our methods together to see if we can help you guys out even more. So what I want to include here for 7.47 is the 7 steps of the creation process that he made. So he bases out, there's 7 steps towards being creative or coming up with new ideas that was originally developed by Plato, but now this is kind of a formalized version for science. So step 1, and so a lot of this is going to seem intuitive, but it's actually really good to know. Step 1, state the question or problem to solve. What are you actually trying to solve? You'd be surprised how many people just kind of, without formally knowing or understanding what it is they're trying to make, will actually just start coding. How many times have you guys done that? I know I have. And I realized, wow, I had no idea what I was actually trying to do. Yep. Okay. So figure out what the problem is. Step 2, research it. You know, in 385, remember what I was telling you guys, like when I was showing you how to build up an adder, right? And you're building off the cells, and I actually showed you that diagram where I drew out the timing diagram that goes into the specific nodes. That's because I was very adamant about, okay, when I draw out a circuit, first thing I want to do is lay out precisely what I need to do. I'm going to name all of the nodes. Now we know they're formally defined as nets here at CMOS. We can name all of our nets. I know it goes into the cells. I know the timing of each one, so then I can figure out how to make all the outputs come out at the exact same time. Research your result. The gathering of data about a specific topic through reading the books, exploring the internet, and I underline this because I consider this very important, and sharing your newly found knowledge with others, presenting it. Part of what should drive you as an engineer is not just making things and making money. Part of it is, and this is when you know you've found what you want to do with the rest of your life, if it excites you and you want to share it with other people, right? That's what drives you, and then you know you've found what's going to make you happy. Is the perfect way to saturate your mind with the elements related to the problem. And sometimes people are going to ask you interesting questions. You know, professors, especially when they're creating a course like this, or creating a course in general, by the 3rd or 4th time, that's when the course is going to be perfect, because the first 2 or 3 times, students ask really interesting questions. And you go, I don't know that. You go, you find the solution, you put it in, you tell the current class, then you put it in so that way when you come through the next time, you go through and you've answered a really interesting question, and that student was probably about to ask it, and then you solved it. You've made the course better because intelligent people like yourselves ask intelligent questions. So the third stage he calls the besta stage. Now, if you've ever been in my office, what's that little thing that I have in the upper right corner? Yeah. What is that? Better is the enemy of good enough. How many times have you tried to design something you thought, I want to do 50 things and start adding little tweaks, but then your customer, the person you were doing it for, says, yeah, but I wanted to do just one thing. And does it do it? No, it doesn't. Well, it has all these fun bells and whistles, but it doesn't do the original thing you wanted it to. It doesn't. Exactly right.
It doesn't tell the time though. But
yep.
it can do this.
It can help you fly. Well, actually, that's kind of cool. But that's when my father was working for he was the chief scientist of submarine launched ballistic missiles for the Naval Surface Warfare Center, and he'd get all these young engineers like you guys are, and they come in with 1,000 ideas on how to improve the missile. Yeah, well, does it launch? We're not sure. Okay, well then you've done too much. So he would point at the sign that says better is the enemy of good enough. This is an important stage. Don't get stuck in the research phase. Eventually you realize you've done everything you can, and then the next step, gestation. Step away. Step away from the problem for a little bit. Think about other things. Go on a date, or if you don't have a date, go play video games, or if you're really lucky, play video games on a date, or whatever you guys like doing. You need to attach yourself to the problem. Instead, give it some space. Look at the problem in a different way with a different perspective. So this is part of the TGO here. I'll get through this in the last 2 minutes. Don't be afraid to think with crazy ideas, and more importantly, don't filter yourself. And he kind of throws what the equation would look like if you were a tree. Because he has an art background, right? So sometimes you're trying to think of it. Oh, what would it look like if it was a tree? And then you realize, oh, hey, you're tying into binary search trees. So that's kind of how that kind of thing came from. Being willing to think outside the box and be silly. Kevin and I were talking about some people at Google said they wanted to fail faster, right? And I'm going to hit on this point. Failing isn't. Don't be afraid of failure. As failure, you take that and you learn, and there's success. Number 5, their eureka moment. Once you realize an idea, document it. Now, this gave me an opportunity to actually quote Mitch Hedberg, which I've always wanted to do in a lecture. It's like, I write jokes for a living, and I sit at my hotel at night, and I think of something funny, and I go get a pen and write it down. Or if the pen is too far away, I have to convince myself that what I thought of ain't funny. So once you have your eureka moment, write it down. Or you can have just a series of small eureka moments, write them down, and then once you have this combined, the next step is bring it into being. Use the tools that you've learned in Advanced Digital Systems and CMOS to do this step 6. And step 7, all the other steps, testing and criticizing. And this is an important point. I've underlined this. Invite criticism. Inviting criticism can be hard. Sometimes it sucks to hear people tell you what your design is not very good. But as scientists and engineers, we have a responsibility to invite criticism of our designs, because ultimately somebody comes up and says, hey, I don't like that part. Actually, you can find, it may help you present a better solution. So these are the 7 steps of creativity, and you can use the tools that you've learned in the courses to help you guys out. So lecture is complete. It is 12:15. Again, I managed to get to the end of what I prepared. You guys fly through this material. Let me close this out.